The recording has begun. I've got your learning objectives. I tried to make them a little bit simpler and more targeted towards the days. Those are up on your Canvas page. If you scroll all the way to the bottom, you'll see the date. Exam number 4 is, I believe, December 4th. Next to that, you'll see a link for learning objectives. I finished your practice exam that I'm going to be linking on there as well. It's up in quizzes. If you want to go access it, you can. You have 999 attempts at it. Each question is rated at 1 point apiece, just for kind of simplicity's sake there. Um, and then I think those were the big action items that I was kind of focused on and thinking that I needed to take care of and tend to. See what else I think. I think that's it. If something else comes up, I'll remember, or I'll bring it up. In the meantime, though, let's go ahead and get started. Back to enzymes. We're talking about enzyme inhibition. Now, we're going to, if you remember last time we talked about competitive inhibitors, we actually kind of talked about all of them, but we're going to take a deeper dive into our different types of inhibitors. And in particular, I remember there were some questions about non-competitive versus uncompetitive versus mixed. And we're going to address those today. So I'm just going to kind of do a quick overview or quick review. I'm hoping that today we will get into enzyme mechanisms, at very least introduce the major components. Now, with that, I'm sorry, I've got a browser that's playing music, and it's actually more distracting than I thought it would be. There we go. Sorry about that. So inhibition patterns. We've got something that resembles a structure. What we're most interested in when it comes to inhibition patterns is what does the inhibitor bind to? And one thing that I want you to think about is how a enzyme inhibitor is designed. Many times they're synthetic molecules, and it's just a matter of, well, what is this? What does the natural substrate look like? Let's see if we replace a hydroxyl group with a sulfhydryl group. This is where organic chemistry in your functional groups is really important, which is one of the reasons why, if you ever are interested in going into the pharmaceutical industry, one of the things that you're probably going to be good at and that you're going to spend a lot of time on is organic chemistry and organic synthesis. So an inhibitor may bind at an alternative site, and sometimes they can do both. We've got our 3 most common types: competitive, mixed or non-competitive, and uncompetitive. Now, here we're going to look at a competitive inhibitor. It competes with the natural substrate. So you can form this EI complex. If ES forms, you're home free. Your product's going to be generated. That's with a competitive inhibitor. If ES forms, that means the inhibitor did not bind to the enzyme, or if it did, it bound and then it released. An uncompetitive inhibitor is, I would say, just for the, kind of like a mnemonic tool, I would say that it's incapable of binding to the free enzyme. With an uncompetitive inhibitor, you're going to form this ESI complex. You're not going to form EI. A mixed inhibitor. Now, a mixed inhibitor, you will many times hear a mixed or non-competitive. And we'll get into what is mixed inhibition versus non-competitive inhibition after a little while. But for the time being, a mixed inhibitor is a molecule that is capable of binding the free enzyme or the enzyme substrate complex. Now, the great question that follows that is a investigation as to, well, I've designed this molecule that's capable of doing both. What does it actually do in practice? What does it actually bind to? Does it bind to the free enzyme, or does it bind to the enzyme substrate complex? Now, in order to answer all of those questions, and in order to understand an inhibitor, you have to do the kinetic analysis. And your kinetic analysis would be to develop a inhibition plot. And so if you remember the other day, I talked about how your trials, the trials that you go through, you're going to have your natural substrate and you're going to increase the concentration of that. But what you're going to maintain constant is the inhibitor's concentration. And so you'll have like one round of trials where you have an inhibitor concentration of 2 millimolar. We'll just say, um, sorry, I got to get my annotate out. Okay, I'm just going to call this round one, where you do a series of different experimental trials. So T1 through T20. Okay. And in T1 through T20, you are varying the substrate concentration, but your inhibitor concentration, just for the sake of simplicity, we're going to say it's 2 millimolar. And it's going to be stuck. You're going to maintain it for each and every one of those trials. Round two, you're going to have T1 through T20 again, and you are going to vary the substrate concentration, but your inhibitor concentration, you're going to increase that for all of those trials, and you're going to call it 4 millimolar. So that's one of the things that you're doing whenever you're doing inhibition studies is you are going through a series of rounds where you'll increase the inhibitor concentration and you'll continue to do that. Effectively, you're asking the question, does this inhibitor do anything? And if so, how does it? What does it do? Now, with that, you'll be able to look at the inhibitor, look at your kinetics curve and come up with, actually, you'll come up with a Lineweaver-Burke plot that stems from a Michaelis-Menten plot. And I'm going to jump over here before we do our first question. On the left, add to the chat what that plot is. The left-hand side, where our y-axis is initial velocity and our x-axis is substrate concentration. Perfect. An MM plot or a Michaelis-Menten plot. Great job, Morgan and Kate. Awesome. And then on the right, well, that's our Lineweaver-Burke plot, also known as a double reciprocal plot. I want you to feel comfortable referring to it as a Lineweaver-Burke plot or a double reciprocal plot. Okay, so you would develop that Michaelis-Menten plot, and here what we see is, well, our inhibitor trials for the olive, blue, and purple lines, those represent where our inhibitor concentration has increased. Now, I'm going to jump back, and we're going to do our first top hat question of the day. How does a competitive inhibitor impact Vmax? Before we proceed, we've got two important kinetic parameters, Vmax and Km. How does a competitive inhibitor impact the Vmax? Let's go ahead and take a look at that. We've got 45 seconds approximately. Clear out all my drawings. Ten seconds. All right, let's look at the right answer. We've got causes it to go up, causes it to decrease, or no changes observed. The correct answer is no changes observed. Now, let me give you a little bit of a suggestion when it comes to kind of predicting this. The easiest thing, whenever I think about inhibition, I always think about a Lineweaver-Burke plot. And I'm going to say LB slash DS for double reciprocal plot. DR, Joel. DR, double reciprocal plot. Now, that plot is going to look like this. You're dealing with your X and Y axes, and I'm going to give myself a green line to represent no inhibitor. Now, the word competitive, for some reason, this is kind of a mnemonic in my head, or this is like a trigger for me to remember this. Um, like 20 years ago, there was a guy he played for the Kansas City Chiefs. He was really good at football and he was really good at running back touchdowns from punts and kickoffs. And whenever he scored a touchdown, he would always put his hands up like this, making an X. And I thought, you know what? I think what he's representing and what he's displaying is that he loves competitive inhibitors because he is a competitor. And so I always think about a competitive inhibitor as, well, I make an X. And my drawing kind of stunk there. I apologize. Let me try that again. I make an X through my y-intercept. So this is the Dante Hall. That was his name. Still is his name. He was a competitor and he was a competitive inhibitor. He would make that X along that y-axis. So if that helps you remember, fantastic. If it doesn't, well, maybe you learned something about former Texas A&M Aggie Dante Hall and Kansas City Chief player. Okay, so that's competitive inhibition. So my mind always goes to the Lineweaver-Burke or the double reciprocal plot when it comes to understanding what is the intercept that I should be looking for, which that's another thing that I want you to think about. I want you to look at these plots and specifically at the Lineweaver-Burke plots and start thinking about where is the intersection? Where is my no inhibitor line and where is my inhibited line? Now, if we move on to look at a competitive inhibitor, you have a Ki, which a Ki is effectively the affinity that your enzyme has for the inhibitor. Now, I'm not going to ask you to calculate Ki's. I want you to know what it is. And effectively what it gives you a measure of, or a kind of comparison of, is how do your kinetic parameters change in a no inhibitor or with the inhibitor. And so here what we have is a no inhibitor line. And then there's your Km. And there's with the inhibitor, here's your new Km. The only parameter that changed in the presence of a competitive inhibitor is the Km. So when we talk about a inhibitor influencing the Km or the Vmax, we refer to this as the Km apparent. And so your Km apparent in this case would be 2. Now, if you increase the inhibitor concentration, well, then your Km apparent is also going to increase. Okay, so just to kind of rehash, with a competitive inhibitor, we care about Vmax and Km. With a competitive inhibitor, Vmax, I'm going to label it as NC, not for North Carolina, but instead no change. Km, the Km in the presence of an inhibitor is going to increase. So your Km will go up, your Vmax is unchanged. Any type of competitive inhibitor is going to display that. The Km goes up, the Vmax does not change. And think about that as like a test question. This type of inhibitor causes the Vmax to remain unchanged, but the Km to increase. Oh, okay, well, that's a competitive inhibitor. I want you to think about that also in the sense of, well, if my Vmax goes down, what type of inhibitor is that? Well, we know that it's not a competitive inhibitor. That's the first thing that we can start from. Do we need to know more information? We do. We need to know what happens to the Km. Now, we'll get into that and we'll kind of put together a little bit more of a table, but in order to do that, let's look at let's look at a uncompetitive inhibitor. Now, an uncompetitive inhibitor, do not mistake that for a non-competitive inhibitor. An uncompetitive inhibitor is incapable of binding to the free enzyme. And so you're forming this EIS complex or ESI. You're making a complex with the inhibitor, the natural substrate, and the enzyme. Those three things, that trifecta is coming together to make something. Now, an uncompetitive inhibitor binds to that complex, but not the free enzyme. Now, what that results in is a decrease in the Vmax and the Km. Okay, so let's think about a decrease in the Vmax. I always think about velocity max, maximum velocity. I think about it like a car. And I think that, okay, this Porsche that used to be able to go 160 miles an hour now is only able to go 140 miles an hour. Okay, so it slowed it down. So its performance has diminished. Okay, that makes sense to me. If I'm inhibiting a reaction, reducing the speed that that reaction can be catalyzed at, that's arguably a good thing. Km, if your Km decreases, what does that say about your enzyme's affinity for the substrate? How does your enzyme's affinity for your substrate change if the Km is going down? It increases. Okay. Now, great job, Morgan. I have a couple of thoughts with respect to that, and I'd like to share them with you because I think that these are relatable thoughts. One, if your enzyme's affinity for its substrate, if the affinity increases, that seems kind of like a good thing. Okay. But let's think about it like this. If the enzyme's going to suck up that substrate a little with a bit more ease, but then it's going slow overall, you kind of have well, it's like one step forward in terms of the effectiveness of the inhibitor, one step forward being that the reaction gets slowed down, but then one step backwards because your enzyme's affinity for the substrate is enhanced. This is also something that's kind of tough to reconcile. Like, the simple question of why? Why is that happening? Well, one reason that I think is helpful to imagine why is whenever you're doing a kinetic study, your substrate concentration is very high relative to the enzyme's concentration. Okay. So you might not be at a saturating level, but arguably kind of in an average chemical reaction or an average enzyme reaction, the substrate concentration is going to be pretty high. So let's say that we have, you know, 10 copies of the enzyme. And I'm going to label this as R1, round one. So in round one, you've got 10 copies of the enzyme. And just for the sake of, nice round numbers, all 10 of them are going to form this ES complex because we know that this type of inhibitor will not prevent the ES complex from forming. 8 of those reactions, so 8 of our 10 are going to go over here. So we're going to get 8 free enzymes and we're going to get 8 products generated. Okay, so that means we got 2 that are more or less locked up or sequestered as a part of this EIS complex. So effectively, then in round 2, when our enzyme is ready to start this reaction again, we've got 8 copies of our free enzyme because 2 of them are still kind of sequestered over here as a part of this EIS complex. Now, all of this is in fluid motion, but what that means is that the relative concentration of our enzyme goes down in comparison to our substrate concentration in that second round. And so effectively, those enzymes, there's less enzyme fighting kind of over the same pool of your substrate. So your Km kind of, in some respects, gets artificially reduced. It's not artificially as it's an illusion or anything like that, but this enzyme, what I'm getting at with it being artificially is that this enzyme in round 1 and in round 2, the enzyme is effectively the exact same thing. It's not like it's got some new binding affinity or new structure or anything like that. There's no new modifications to the protein. You've got 8 copies of the enzyme going after, well, still a kind of large concentration of the substrate. And in round 2, well, we're probably going to have, let's say, another 2 copies of EIS form. And so then for round 3, you've got only 6 copies of the enzyme. Now, that's the kind of reasoning. I'm going to clear all my drawings here. The important takeaway for this, though, is that what happens to your kinetic parameters? In an uncompetitive inhibitor, both the Vmax and the Km will decrease. So if we're kind of keeping tabs with things at home, we've got a competitive inhibitor, which causes the Vmax to not change, the Km to go up. An uncompetitive inhibitor causes the Vmax to go down and the Km to go down. So from there, we can kind of address this and kind of figure this out. Like, even if we were to, what this is showing, this model on the lower right-hand corner, is if we were to increase the substrate concentration, we're not changing anything. The enzyme is still going to go on to make the product. Your kinetic parameters aren't going to change. Your Vmax is not going to change even if you increase the substrate concentration, because it's not a question of can the enzyme bind the substrate. Instead, it's a question of, well, when that enzyme binds the substrate, what happens? What's the fate? So the effect of an uncompetitive inhibitor cannot be overcome by high concentrations of the substrate. And this is a note that is important to recognize because this is in contrast. I'm going to draw a little star. Contrast to a competitive inhibitor. Okay. Now, what does that ultimately look like on a graph with a unchallenged, so no inhibitor present and inhibitor present? What we see is we see a pair of parallel lines. So the top line represents trials with the inhibitor present. And what we see is that these 2 lines basically run parallel to one another. If you were to increase the inhibitor concentration, what's going to happen is you're going to get another line. So this would be plus, I'm going to say 2I, so 2 times the inhibitor concentration. So if we're thinking about our graphs, and again, this right here is a Lineweaver-Burke or a double reciprocal plot, as evidenced by the 1 over velocity, that's a reciprocal value, and then 1 over substrate concentration, another reciprocal value. This is our Lineweaver-Burke double reciprocal plot. We have a competitive inhibitor by contrast that looks like this. Boom, and then here's my other line. So no inhibitor plus inhibitor. Okay, so I like to kind of take these piecemeal of like, let's look at the individual graphs and think about them and reflect on them. So we've got a competitive inhibitor, we've got an uncompetitive inhibitor. What structures can form, or what kind of complexes can form? The EI complex will form with this type of inhibitor. And then the ESI or EIS, those are kind of interchangeable. Okay, now we're going to look at basically how you would calculate. But again, KI calculations, I'm not expecting you to do that. But this is a way that you could calculate your Km apparent and your Vmax apparent with a inhibitor present. And then you could calculate the Ki. So again, your Ki is effectively your measure of affinity that your enzyme has for that inhibitor versus the substrate. So if you have a very high Km, that means your enzyme has a very low affinity for your substrate. If you have a very low Ki, that means your enzyme has a very high affinity for your inhibitor. So now we're on to what I would argue and what I would say is kind of the trickiest of the bunch. And that is your mixed and non-competitive. And the reason that these are grouped together is because it's actually just kind of one idea. But then what are the results? That's the question that's being asked. Okay, so a mixed and non-competitive inhibition. Now, this is an inhibitor that can bind to both free enzyme and the ES complex. Okay, so this is one thing that's kind of tough. Um, there's like a design, and then there's execution. And let's hang out in this design space. So this is where you are working on a team of organic chemists and enzymologists, and you work together and you design a molecule and you say, hey, this molecule, based on the structure of our enzyme, the structure of our substrate, this inhibitor, it can bind to E and it can bind to ES. So this is the design. You've you looked at the molecule and you say, okay, I'm going to put this carboxyl group here and a sulfhydryl group here. This carboxyl group will be attracted to the active site, so it can compete. But then the sulfhydryl group, in concert with this carboxyl group, well, that's going to still allow the substrate to bind. So it's kind of like you designed it to have both effects. So your idea is almost, well, I'm going to design this enzyme to act as or I'm going to design this inhibitor to act as a competitive inhibitor and an uncompetitive inhibitor because I want it to do both things. And so that's where that term mixed comes from, where it's effectively a mixed type of inhibition. Now, this is again, you've designed it to do this. You've looked at the molecules, you've looked at the enzyme, and this is what you're expecting and wanting to happen. Now, the question is then, and I've always heard this phrasing in uh, space shuttle launches. There's a design flaw and a launch flaw. Okay, well, the design flaw, or not necessarily flaw, but there's a design issue versus a launch issue. Um, was there a fundamental problem with how you designed them all, or the spacecraft, or was it, on launch day somebody forgot to Velcro that thing? I just know that NASA developed Velcro, I think, or maybe it was 3M. At any rate, here we are. So the inhibitor in this case has been designed to do both. That's what you're expecting. It's what you're wanting. Now, the affinity of the inhibitor to the two complexes might be different. So it's almost like that inhibitor that you designed might have a preference almost. It might be more attracted to the free enzyme than the ES complex. Now, if binding of the inhibitor, okay, so our inhibitor changes the affinity for the substrate, our Km is going to be changed, and it will be called mixed inhibition, which let's think about this. Let's think about our Km with a competitive inhibitor and an uncompetitive. How does the Km that an enzyme has for its substrate change with a competitive inhibitor? First of all, does it change? With a competitive inhibitor, the Km absolutely increases. Great job, Micaiah. Sorry if I mispronounced your name. Um, an uncompetitive inhibitor. What does an uncompetitive inhibitor do to the Km? Oh, awesome. Thank you. Great, great. What does an uncompetitive? Absolutely. Okay. So now let's look back at this definition. If binding of an inhibitor changes the affinity for the substrate, Km will be changed. Okay. So this is kind of like ambiguous language. It's almost like, hey, it changes. That's almost like where yeah, you're trying to explain something and you don't really, you can flip a coin and you're like, I can't remember which one it is. Well, it is definitely altered. It definitely changes. But in this case, this is saying that the Km could go up, it could go down. Okay, so again, we've designed this molecule to bind to the enzyme, to bind to the enzyme substrate complex. We do our kinetic studies and we see that the Km changes. Maybe one time we do it and the Km goes up, and then another time the Km goes down. Now, where do we go with this? What we want to continue to investigate is, well, what happens to the Vmax? Now, we've got this other situation. If only the Vmax is affected, it is called a non-competitive inhibitor. Okay, so again, we've designed this molecule to bind to E and ES. And we look and we see that only the Vmax has changed. So if we were to say Km, no change, and Vmax changes. And I say changes because, your Vmax could, more than likely it's going to decrease, but could it go up? Potentially, potentially. Okay, so now what we've got is these items here are basically saying, well, this is what a competitive inhibitor does, and this is what an uncompetitive inhibitor does. Now, oh, sorry. This combination right here, Km does not change and Vmax changes. That would be non-competitive. Okay. So then when we go on, this next slide, we're going to clear out all our drawings. These two plots right here, what do they show? These two plots show us, well, and actually here, you can look at these two plots and ask the question, or be asked the question, independent of the label on there, just say, is this a non-competitive inhibitor? And to answer that question, all that you need to do is you need to go to the y-axis. You see, okay, Vmax, Vmax, they're different. Vmax, Vmax, they're different. Okay, so in that case, we have we do not have a non-competitive inhibitor. Now, what I want you to look at here is this plot right here shows our inhibitor is absent. So it's unchallenged, okay? Then we want to look at this one. What happens to our Km? Well, the x-intercept gets closer to 0. So the Km, in this case, what I prefer to do here is I prefer to put numbers down. So I'm going to say this is -5 and this is -4. Okay, so then -5 equals 1 over -1 over Km. That means my Km is 1 divided by 5, or 0.2. Okay, and then here, -4 equals -1 over Km. And that would be my Km equals 0.25. Okay. So in this case, my Km goes up. What about my Vmax? Well, my Vmax here and here, let's call this 1, and then let's call this 2. So Vmax in the presence of my inhibitor, oopsies, that. My Vmax goes from 1 over 1, which is 1, and 1 over 2, which my Vmax equals 0.5. Okay, so if your Km goes up and your Vmax goes down, well, that would be an example of a mixed inhibitor. Now, if we look at this combination over here, well, what happens to our Km? In the presence of our inhibitor, we've got, okay, so again, this is -2. I'm going to call this -3. So Km equals, so I'm doing this math kind of quick. -2 is equal to -1 over Km. And I do the algebra and I find out that my Km is 0.5. And then for this one, my Km, -3 equals -1 over Km. My Km equals 0.33. Okay, so in this case, my Km, what's it doing? My Km decreases. What about my Vmax? My Vmax, again, we'll use 1, and then we'll use 2. Well, my Vmax goes from 1 to Vmax equals 0.5. Okay, so my Vmax also goes down. So thinking about all of the different movements of my Km and my Vmax and my Km and my Vmax, there's a lot to keep in mind. Now, if I were you and I were preparing for this exam, knowing these graphs, understanding these graphs is very important. Being able to look at a graph and say, well, that's a mixed inhibitor because the Km goes down and the Vmax goes down. Oh, and that's also a mixed inhibitor because my Km goes up and my Vmax goes down. Now, the other variable or the other situation that we can talk about and that's relevant is what happens to, in the case of our, there we go. Oh, let me clear all my drawings. So this is effectively what we've talked about. Our decrease in Vmax and an increase or decrease in Km is a hallmark of a mixed inhibitor or of mixed inhibition. Now, the effect of a non-competitive inhibitor can only be partially overcome by higher concentrations because remember, it has some elements of it that make it similar to a competitive inhibitor. Now, I'm going to skip over this just because I'm not asking you to calculate that. Instead, what I want to show you is this right here. In this plot, looking at this plot with no inhibitor and with the inhibitor, how does my Km change? No change. Perfect. Morgan, how'd you figure that out? Which axis did you look at? The x-axis. Perfect. Perfect. Wonderful. So what you can take a couple of different approaches to looking at this and evaluating an inhibition plot. You can look at, let's say our two lines intersect on the y-axis. What type of inhibitor is that? So whenever you have a question like this, go ahead and Morgan, close. Wait, yeah, competitive. Sorry. Yeah. Morgan, you were so close that you were actually right on top of it. Sorry about that. Yes, you're absolutely right. It's a competitive inhibitor. Now, then thinking about it as, okay, what about if my lines intersect on the x-axis? Well, then I have a non-competitive inhibitor. What if my lines don't intersect at all? That would be an uncompetitive. So I'm going to jump back to show you that one, but I don't need my pen function. Nope, I can do it this way. Here's my lines not intersecting at all, a hallmark of an uncompetitive inhibitor. If my lines intersect, and I'm going to take you on a little bit of a journey back to maybe like I think for me, it was a pre-cal class. Some people might have taken it as a trigonometry class. When you look at a XY coordinates, you've got quadrant 1, quadrant 2, 3, and 4. And I'm like 98% sure those are my numberings. So if my intersection is in quadrant 2, that's a mixed inhibitor. if my intersection is in quadrant 3. That's also mixed inhibition. So I always like to think about it almost as lines no intersect. If they don't intersect, that would be uncomp. Intersect, quadrant 2 or 3. And is there anyone who can vouch for me that those are quadrants 2 and 3 that I'm referencing? That would be mixed. And then x-axis intersection would be non-comp. Yes, I knew it. I knew it. 41-year-old Joel is just as smart as 17-year-old Joel. Maybe or at least I remember something I learned when I was 17. If our coordinates intersect on the y-axis, then you're talking about a competitive inhibitor. I think that this is really an effective way. Like, if you're thinking, okay, I need a forearm tattoo before the next exam, this might be a pretty good one to get in terms of helping you understand and helping you recall basically what types of competitors you're looking at. Now, one of the things that I want to stress before we proceed is these are looking at the plots. And remember, whenever I was talking about design versus execution, the important point here that I want you to appreciate is you may be designed a molecule to be a mixed inhibitor, but until you plot this out, until you do those kinetic analyses and determine how your Vmax and how your K are impacted, you wouldn't classify it as that. So you've designed the molecule and you think, oh, it's going to do this, this, and this. Perfect. That's going to be an uncompetitive inhibitor or a non-competitive or a mixed. But until you actually plot it, you can't really say with much confidence that's what it does. So this is where, the classification of a molecule, of an inhibitor, is based on your kinetic analyses, based on these catalytic studies. So there's always a little bit of a disconnect because, oh, well, this is what I designed it to. And if I look at it, oh, it looks exactly like the natural substrate. Not until you do the experiment can you really classify an inhibitor. Okay, now I wanted to do, I think I got one top hat question here at the end, and then we're going to go on to mechanisms and get into them just a second. So in the presence of an inhibitor, the Km does not change, however, the Vmax does. What type of inhibitor is this? So I'm going to start the question, but while the question's running, I'm going to talk to you a little bit about this. So in the presence of an inhibitor, the Km does not change. Okay, so that means we've got an intersection on our x-axis. The Vmax does. Okay, so x-intercept or x-axis is where our intercept is taking place. Well, if it were the y-intercept, that would be a competitive inhibitor. Not the case. If it's in quadrant 2, it'd be mixed. If it's in quadrant 3, that would be mixed. So we're left with either uncompetitive or non-competitive. And what is the uncompetitive incapable of doing? And what does that plot look like? I think that's a good way to answer the question. Okay, we got 32 answers. We're going to check the correct. Guys, all y'alls. Wonderful. That is fantastic. So happy to see that. Now, that's awesome. I'm super proud of you. Great job. You should be proud of yourselves as well. Okay, now I'm going to pause my share because I'm going to jump into enzyme mechanisms, catalytic mechanisms. We've got one question that I want to get through. And let me just say, if you are a fan of organic chemistry too, well then this is your your jam. Um, if you're not a fan of organic chemistry too, don't worry, this is your jam. In part because, I'm sorry, Morgan. Yes, I know. In part because we have fewer options. My memory of organic chemistry too was a couple of things. One, a Huckel structure. I remember that. I remember the Diels-Alder reaction. And then I remember it was like, well, you got your Grignard reagent, you got this reagent, you got this reagent. Oh, well, this one does this to chlorine, and this one does this to bromine. And I know those are both halogens, but organic too, I really struggled in because I felt like there was just so many different options. And in terms of like catalysts, and that I struggled with that. Um, in biochemistry, we're talking about amino acid side chains being involved in kinetic reaction or in catalytic mechanisms. And so if you think about your different amino acids, um, one thing that you really don't have to worry about is an amino acid like leucine doing much of anything. Because what's leucine's side chain really capable of? Not much. It's a non-polar residue. So when it comes to catalytic mechanisms, enzyme reactions are described in the same way as non-catalyzed reactions. We have basically some electrons that get pushed from this partial negative group to this partial positive group. And from there, we form some sort of intermediate, and that intermediate has a full-on positive charge. And then at the end of the day, we get a water out of it. Now, is this a specific reaction that you're going to need to know? No. But I just want you to look at this and think, okay, I've pushed electrons before and I get it. That's, I've got to find out which are my electronegative groups and which are my nucleophiles and electrophiles, and you're going to be in good shape there. Now, there are three basic enzyme mechanisms. So this is also something that I think is a fantastic change from organic to biochemistry. You got three options, and those three options are acid-base catalysis, covalent catalysis, and metal ion catalysis. Almost everything that we look at in terms of enzyme mechanisms or an enzyme mechanism is going to fall into only one of those categories, is going to predominantly be classified by one of those categories, or it's going to have a little bit of each one of them. Now, with that, based on, I want you to have this top hat question. Think about amino acid R groups and think about a definition of an acid or a base. Um, Based on, what is an acid? What is a base? Well, we got protons moving around. That's about it. Now, based on the side chain, so the R group, which amino acid can act as an acid or a base? It can donate protons or accept protons. Aspartic acid, leucine, methionine, phenylalanine, aspartic acid. There's a couple of different options there. We're talking about just the side chain, not the N termini or the C termini or the peptide bond. We're just talking about the R groups. Again, we got aspartic acid, methionine. Ooh, methionine. Ooh, that's tempting because that's got sulfur, right? Oh, but sulfur with a methyl group. That's not, it's a little bit less appealing. Phenylalanine. That's a ring. And C. Great. This is one that's kind of got to tell. Which which of the molecules with the name acid can act as an acid? You're right. It can act as aspartic acid can act as an acid or a base. It all depends on the pH. Okay, now I'm going to show you this slide. Well, acid-base catalysis is involved in all enzymatic reactions involving proton transfer. So movement of a proton, donating, accepting. And we are at 9:50 a.m., so I'm going to go ahead and stop. But I want to say a couple of things. One, thank you guys very much for coming to class. We do not have a lot left this semester, so thank you guys for your persistence and staying with everything. Um, I hope you guys have a great Wednesday, and I will see you again Friday morning, and we'll kind of continue from there. All right. Have a good one, everybody.